Thank you for joining me today to continue our further investigation regarding greedy algorithms. I'm going to write here greedy algorithms. And essentially, the first conversation today is to recap greedy algorithms. So essentially, why we want to recap this is because we have already deliberated about that, and we have seen a couple of examples regarding it. So my intention right now is to essentially go through some of techniques that we went through, create some sort of summary about it, and then from there we derive a few, what I might call hallmarks or properties of grid algorithms. Then we sort of try to formulate multiple problems arising from there. So what did we discuss last time? We went through a couple of techniques. One of these techniques was single source, shortest path algorithms or algorithm. In our case here, we discussed the famous Dijkstra algorithm, and we use this algorithm to calculate a single source shortest path where the weights of the graph have been given. So this has been on a weighted graphs. Okay. Now, one important thing actually we saw about this single source shortest path algorithm is that if all the weights were equal, so if you say if all weights in the graph were equal, or what we might call uniform weights, okay, uniform weights across the graph, then, well, instead of using Dijkstra algorithm, which was using a priority queue to do all the work, we could just use BFS, and this would just use a normal first in, first out queue. Okay, so we could have born to the problem of the single source shortest path if all the weights in the graph were equal, or if we had uniform weights using BFS technique, and in this case would be just using the normal queue as well. Okay, now please review these notes because we have them on Canvas and we have them on my Google Drive to be able to see how we could use these kind of techniques. Now, another thing that we investigated, again, with respect to grid algorithms, was this idea of generating what we call minimum spanning trees. Minimum spanning trees. And in this case, we investigated, just two techniques. One was called Prim's algorithm. We're going to revisit them just in a minute by just drawing one graph. Prim's algorithm, and we also used a technique called Kruskas algorithm, and so on, and Kruskas algorithm. There's another technique called Boruvka's algorithm as well that could have been used. I would urge you to go investigate this, how we could use, or how this technique is used, how this technique works, and so on. For this case of this particular class, I'm just investigating these two things. But as I mentioned multiple times, it's always good to go ahead and investigate, numerous techniques because understanding and creating these new techniques allows us to know more. Okay, so what I want to do maybe initially is to investigate how we could use any of these techniques that we have. So I'm going to go through Prim's algorithm quite quickly, Kruskas algorithm, and then this would enable us to essentially to go back to the materials that we have discussed in the past. So Prim's algorithm, and this technique essentially is to get what we call an MST tree, okay, minimum spanning tree. Now, let me draw a graph here. I'll say this is A, this is B, and I'm just going to say this undirected graph. So I'm going to put some weights to it. Okay. Just to go A, B, C, D. I'll give it a value of 3 here. I'll give this a value of 6. I'll give this a value of 2, and I'll give them a value of 4. So if you look at this graph here, which is a nice graph here, it's a weighted graph. It's an undirected graph. Does it form cycles? Yes, it has cycles because we can move from A to D to B, back to A. So we could do A, D, B, A. We could do A, B, D, A. So these are sort of a cycle here, and so on. And there's another cycle here, actually. We could do the same, D, B, C, D, D, C, B, D, and so on. And then there's an outer cycle, and so on. So it forms 2 cycles, and so on. Now, we could generate a minimum spanning tree for it, but specifically before even we think about minimum spanning trees, in the past, we used DFS to come up with a spanning tree. We used BFS to come with a spanning tree. We could use a Dijkstras algorithm to come with a spanning tree. The only difference being that those spanning trees, because we generated them from techniques that essentially are powered for doing a search, instead of creating actual minimum spanning trees, they will create spanning trees that might not be minimum spanning tree. There are spanning trees which are not minimum spanning trees. For instance, if we're just thinking about this graph, what are we interested in with respect to spanning tree? So a spanning tree in general, if you're just thinking about a spanning tree, which is not a minimum spanning tree, a spanning tree in general would essentially have all vertices in the graph, Okay, so the set of 4 graphs. And then we'll need to have a subset of edges of the graph, a subset of the edges of the graph. Maybe I might tease you and ask you, what is the size of this subset, right? You know, like if I said here, E, small e, which is a subset, is in, or is a subset of E, which is the graphs, maybe the first question should be, what is the cardinality of E, right? What is cardinality of E? Now, remember one thing, we are forming a spanning tree, and we need to connect all vertices in the graph. We need to connect all the vertices in the graph. One thing we know about trees in general is that they are direct acyclic graphs. You know, essentially, they do not have cycles. Okay, so now going with that, then E, the set of edges that we need in order to connect all vertices should be really the vertices minus 1, right? We need V minus 1 edges to connect all of these. So for example, you know, a spanning tree here would have been just A, B, D, and C. We could just draw this, and essentially this is a spanning tree. It connects everything. Look, we only needed 3 of them. Look at this. If I added any more edge, again, I am creating a cycle. So we know for sure that the number of edges that I need to connect all these 4 vertices is 3, and so on. Okay, you know, we could draw another one. For example, we could have A, let's draw another one. I'll take a red pen now. Have A, B, D, C, exactly like that. And then I could do that, something like that. I could do something like that. Okay, that's also a spanning tree from the graph. I'm not saying minimum spanning tree. I'm just saying this is a spanning tree of the graph that we have here. Okay, now somebody might ask us also, how many spanning trees can we generate? Yeah, that's another important question. So this was how many edges we need. Maybe another question could be, how many spanning trees can we generate? How many spanning trees can we generate? Let's think about that for a minute. How many spanning trees can we generate from the tree? Think about that for a minute. I'm going to redraw here as you think about it. Okay, our graph looks something like this: A, B, C, D. We had this edge, we have this edge, we have this edge, we have that edge, and we have that edge. Okay, and then this was 5, this was 2, this was 4. Are you still thinking about it? And then this was 3, and this was 6. So this is our graph that we formulated a few minutes ago. So the question that I have, how many spawning trees? I'm not going to say minimum. That's another question. How many spawning trees can we generate? Good question. Now, remember what we said. We said we have E, we need E edges, which is a subset of E, the total number of edges that we have. And then we said the cardinality of E must be equal to V minus 1. You know, we need V minus 1 edges, number of edges to connect all vertices V. Okay, so that's the one we need. So how many vertices do we have? You know, the question that we should be is how many vertices, you know, how many, so we need to know how many vertices we have in order to know how many edges we need. And then I think we're just selecting a combination of edges, small e, a combination of edges, small e, in order to get this particular graph. Now let's consider two things. Supposing our graph did not have this edge here. So now we have only 4 of them. So how many of these can we have? How many spanning trees can we have if the graph looks something like this? Well, we could have something like this. We could go that side, and that side, and we are done, right? That's one way. Another way could be, we could have gone this way, we go that way, and then we go that way, and we are done. Another way could have been, we go this way, we go that way, and we go that way, and we are done, right? So these are the multiple different ways of doing that. So what are we doing? Out of these 4, we are selecting 3 that connects everything. So essentially what we are doing is we are saying the number of spanning trees, maybe I would say cardinality of spanning trees is, the cardinality of spanning trees is all the edges that we have, and then choose E, where E is this one, where E is this guy here now. So in our case here, for example, this one, the total number of edges were 4, and here we have 4, choose 3, exactly, 4, choose 3. So in our case, this will be 4 factorial over 3 factorial, and then 1 factorial, right? And 4 factorial. So essentially, this will be 4. The answer would be 4 in our case. Okay, is it 4? Yeah, I believe so. We will have 4 of our case. How many did we generate before? We had, we can redraw them. I mean, they're on a form. So we have A, we have B, we have D, then we have C. So one of them could be this one. Another one could be A, B, C, and D. This could look something like that. Another one could be A, B, C, and D. And we have considered that. We have considered that one. Oh, we have considered this one too. So that should not be the case. Okay. Oh, we have considered this one. We hadn't considered this one. And then we can have A, B, C, and D. Then we consider this one, and a bit of that one, and so, and so on. So something like this. Okay. So 4 factorial. Now, what happens when we have another edge now connected here? We have another edge connected here now, supposing we give this 2, then now we have a small situation, because now we can form multiple minima. And we are forming minima because we have, we have this cycle being formed here. And then we have this cycle being formed here. Essentially, we have 2 cycles being created from this graph and so on. So this edge could be used, in any of this manner. So when this is the case, then the cardinality of a spanning tree is going to be given by now the total number of edges. Choose the number of edges that we need, the v minus 1, minus the number of cycles. Okay, minus the number of cycles. So here the number of cycles would have been 2, so it would have been 4 minus 2. So we could have 4 minus 2, we could only have done 2 actually from this case. So it could be, this would have been generated 4 minus the number of cycles is 2. This would have been 2 only. Is that the case? Let's try to formulate this now. Okay, we could try to formulate this now, or you could try to do that at your own time. You negate the number of cycles here. Again, look at this. We'll have A, B, C, and B. One way of doing that. I believe we could have all these ways. And then now we can have our cycles already being formulated by using the graph that we have, as another way of doing it. Okay, and so on. So we would be able to generate the number of cycles formed by this one. Okay, so this would have been, remember here, okay, sorry, because we're increasing this, the number of edges, sorry about that, the number of edges now increases 1, 2, 3, 4, 5 edges. So this would have been 5, choose again on a 3, and this now would have been 5 factorial, 3 factorial, 5 minus 3 is 2, 2 factorial, minus 2, and essentially this should have given us some numbers. So this will be 5 times 4 divided by 2, which will be 10 minus 2, so the answer here would have been 8. Sorry, yeah, minus 8. This would have been 8 here. Okay, so this is how you know how many of these edges that you are going to have. And it's important to know that so that you can be able to think about what's the time complexity of either generating all these things or thinking through how to come up with them. The question is, supposing you wanted to know, supposing you wanted to carry out a brute force determination of what or how many minimum spanning trees a tree has, then you'd essentially be able to know by knowing how many of these that you are forming. Okay, I'm hoping that's understood. So let's go on. So that was a caveat essentially just to show us how many of these minimum spanning trees that we have. Now, the next thing is to think about minimum spanning trees. And the minimum spanning trees would be some trees of total minimum weight out of these sets of mini spanning trees that would have made from a graph. So that's what we are going to start off with. So again, let me redraw the graph, A, B here, C, D, and have those kind of things going on. So this was 2, and we go back here, this is 5 and 6, 5 and 6, and then 4 and 3. So those 4 and 3. So I am not going to go back to sort of revise a lot more regarding the techniques that we have carried about, essentially going back to reformulate the entire working of it. But what I'm going to do is demonstrate how we could go about creating the minimum spanning trees. So I'm going to start off by talking about Prim's algorithm. Again, we have seen this in a previous class, so I'm just going to recap it, and then you have an exercise about it. Okay, Prim's algorithm. Now, with this one, we want to have a starting point, right? So this is, okay, is constructing a tree, construct a tree from a single point. Okay, we want to construct a tree from a single point. Now, single point could be arbitrary, right? Arbitrary, or we could be a given arbitrary point. And I'm saying arbitrary points, and I'm saying this could be given. Why is that? Well, that is because all vertices must be connected. So we could start with any vertex, right? Because all vertices must be connected to our tree. So we could start with any one of them. Or I could give you, as your professor, give you one particular vertex to start, and so on. So that's essentially how it works. We start with an arbitrary vertex, or an arbitrary edge could have, arbitrary vertex, not edge, arbitrary vertex, and so on. So, well, we could say we're starting off from A. Okay, we could say we're starting off from A. Now, let's think about it. We're going to have two things. We're going to have two things. I mean, really like that. It feels great, right? To put two things here. We're going to have two things. We're going to have the tree being formulated, and essentially we have our graph, right? We have a graph. And instead of actually having a graph, previously, what we have done, instead of essentially working directly with a graph, we created a temporary sort of data structure. For example, working with Dijkstras, we created a priority queue. Working with BFS, we created a queue, and so on and so forth. So in this case, we want to work with, I'm just going to call it a frontier. Then we can think about what this frontier is. And this frontier is going to keep for me all things within the graph, all things within the graph that have not been used to create the tree. Okay, maybe I could say frontier, keep all vertices that have not been used, in the tree. Okay, so if we consider the tree to have T vertices, then this frontier is essentially keeping, so supposing the graph has VE of edges, so our graph has VE with V vertex. So the frontier will have the subset of all vertices which are not in the tree. So tree contains some, at the moment, or in the beginning, T contains some sort of subset of vertices, and then VT is, or maybe I can say all the vertices minus what is the tree, all the vertices minus what is in the tree. Also, this is also written like this. Okay, it's also written like something like this. So we have a cut of vertices which are not in the tree, So if you think about it, in the beginning, the tree is empty, does not have the vertices. And essentially, our frontier could have everything else, right? Everything else which is not in the tree. The tree is an empty set at the moment. Okay, so this is number one, good to understand. Now, if we are going to say that the frontier has V minus T vertices, then we need to keep them somehow, or we need to identify them in a way, okay? So the way this technique works is similar to Dijkstras algorithm. In the context is, we start off by assigning each vertex a value, a large value. In this case, a value which is going to be positive infinity, okay? So what we're going to do is, if we pick one, construct tree from a single point, arbitrary point. If we have a single point, that single point will have the value, for example, in this case, 0. And we're going to label everything else as having positive infinity, something like that. Now, this should be able to now start telling you what kind of thing that our frontier is actually going to have. So now we're starting off from A, and everything else have been put into infinity. And all those things now, we're going to put them into the frontier. And then to create our tree, what we're going to do, we are going to pick something, pick vertex in our frontier. The frontier, we can think about it as F. Pick V in F. Pick a V in F with the lowest value. right? With the lowest value. So in our case here, the lowest value is A. So we're going to pick A, the one with the lowest value. Now, once we pick A with the lowest value, remember this is going to be, the priority item, so to say. It has the lowest value. So we pick A with the lowest value, and then this is what we are going to do for all neighbors of A, for all vertices adjacent to the V that we have packed. For all vertices adjacent to the V that we have just picked, we're going to calculate like this. I'm going to say if the key of V is less, if the key of V is greater, if the key of V, so we started by assigning all the keys as, each vertex a value or a key of infinity. So we're saying pick V in F with the lowest value. We pick, for example, A. And then for all vertices adjacent to V, if the key of that vertex is greater than the value between the V that we have picked. So maybe we should call this U so that we don't get confused. So we're saying if the key is bigger than the weight between U and V, so essentially the weight, the edge, then update key of V as being the weight, then copy and paste. That's all, then copy and paste. So let's imagine this. We picked up A here. And now A, what are the vertices adjacent to A? Remember, this is the degree of A. The degree of A is 2, and the vertices next to them is B and D. And therefore, we find from A to B is 5. 5 is smaller than infinity, so we update this infinity. And then A to D is 4, so we update this 4. Okay, so now the things in our frontier now here, we have already popped out A and made it part of the tree. And then we have D, B, and C in the frontier. We updated D and B. Now, remember, think about what data items or data structures that we'd have. We're going to update D and B, update their value. So from being infinity to now the value 4 and 5 as demonstrated here. Then I mentioned copy and paste. So what is copy and paste? Now repeat this process, pick up from the frontier the lowest value item. So in our lowest value here is that we are going to have D and B and C. The lowest value is D with 4. So we're going to pick D here. Okay, D here because it has the value 4. Okay, we pick D, value 4. Now let's imagine from D now that we have picked, we're going to carry out the process we needed before for all the adjacents, all the vertices adjacent to D. Let's update them. So from D to go to B is 2. D to B is 2. So now we have to update these. 2 is smaller than 5. So we update these to 2. And then D to C is 3. 3 is smaller than positive infinity. So we update this to 3. There we are. We update that to 3. And I believe we are done with D. Okay, we are done with D. Now, we check again what we have. We have a couple of things in our frontier now. Remember, in our frontier now, A and D are no longer in our frontier. They are done. So we are now going to check, what is going to be top in our frontier. Top in our frontier is going to be B. It's going to be B because it has the value 2. So we pick B. So it's going to be B here. It has the value 2 here. Okay, it has the value of 2 here. So we pick B now because it has the value of 2. Now, B is already added in and essentially popped out from the frontier now. And then now from B, we want to update the other values. Okay, now D is already in the tree. We can go back there. A is already in the tree. We can't go back there. So the things which are remaining is what? Is only C which is remaining. Okay, now from B to C is 6. 6 is bigger than 3, so we cannot relax that, that edge and so on. We can't do that. So we are going to pick the value from D to C, which is will give us the value of 3. So there we are. We have all the vertices in the tree, A, B, C, and D. And then we have picked the most minimum wedges to connect them. And here, our MST now, the MST tree is this one. And the value of MST, the value of MST is 9. Is 9. Does it make sense to everybody? So we're going to practice that, how to do that in a few minutes with using a quiz or so. So just have that in mind of what we did here. Important tree is that we started by constructing a tree from a single point, from a single point. We built 2 sets, a set with a tree, which initially was empty set, and then we created a frontier. We did this frontier by first labeling all the vertices in the tree, apart from the single point. The single point we labeled as 0, and all the others, we gave them the value of positive infinity. And then we kept updating them using this formulation that is down here. Using this formulation that is down here. Essentially, if the key of V is greater than the weight between U and V, then we updated that key of V is the weight between U and V, and so on. Then we updated this point. Okay, so why is this a greedy approach? It's a greedy approach because from A, we are only interested with the value that minimizes the weight between the edges. So the edge that we have just from A to D is 4. We are going to pick that up. And essentially, we are solving a sub-problem of the tree by picking up the most minimal edge. And then we are assuming that, well, if that is the case, that's the weight is the minimal, then that must also be a formulation or will be part of the overall global optimal solution, essentially the actual tree that we are going to calculate there. So that's the idea that we are following the whole time. So we are picking one solution. We came up with the idea, the rule of the thumb, and the rule of the thumb was pick, given a particular vertex, pick the edge that has the minimal cost, then move on. Repeat, copy and paste, as I keep saying, copy and paste. And then we formulate this. The belief that we have is by picking up the most minimal edges, we are going to return up with the global optimum that has the minimum cost of the tree. That is the Prim's algorithm. Okay, I'm going to redraw this graph, and then we're going to do Kruskas. Okay, this is A here, and this is B. This is 5. This is D here. This was 2. I believe this was 4. This was 6. This was C. I believe this was 3. Okay. So these are things that we have. So this was Prim's. And here now, we are going to do Kruskas algorithm. Kruskas algorithm. Okay. Let's think about Kruskas algorithm. Now, Kruskas algorithm will work almost the same as Prim's because they are basically being used the same thing, with a subtle difference, one big difference, that we're going to form a forest of trees. Forest of trees. Forest of trees. It means that we are not always going to be connected. The graph or the trees are not always going to be connected. The trees are not always going to be connected. And because we are forming a forest of trees, keep in mind the forest of trees, the most important thing here, instead of considering the vertices, we shall consider only the edges. Shall consider maybe both edges and vertices. We're going to consider both edges and vertices. Consider both edges and vertices. This is what we are going to do. We're going to pick all the vertices, and for each vertex, we are going to create it as an independent set. That's what I mean. We're going to have A as a set, B as a set, D as a set, C as a set. Okay? We could think about it as possibly just forming a set of V vertices, each on a single point. And then we are going to consider all edges. Now, edges, we can consider them as a tuple, and we're going to consider how many edges do we have. Listen to this. We have A and B, for example. I'll say A, B. We're going to have AD. It doesn't matter how I start them. I'm just going to consider them. AB, AD, AB, AD. We have BD. We have BD. We have DC. We have DC, and we have BC. We have BC. Now, let me label the point. A to B is 5. Let me just put those weights here. A to D is 4. B to D is 2. D to C is 3. And B to C is 6. Now, think about it for a minute. So I have all those edges in there. And what I'm going to do, again, using this idea that I have some sort of frontier, I am just interested in forming a frontier using my edges. Okay, so I'm going to be removing the minimum edge, the edge with the minimum cost, and using it to form for me a tree. And therefore I can form multiple trees. This is why I said a forest, because essentially, well, I'm just picking up an edge. The caveat here is once I consider an edge, I'll pick the vertices that just incident to that edge. I'll consider I'll pick the vertices. I'll pick the vertices incident to the edge and unify them or merge the sets. That's what I'm going to do. So let's take an example. So which one has the smallest cost? BD. BD has a size of 2. So I could have drawn this. A, B, C, and D. I'm just forming a tree, A, B, C, and D. It doesn't matter how the tree looks like. So I have A, B, C, and D. I'll pick the edge BD because it has a value of 2. So I'll have put all these things in some sort of frontier, and I'm just going to pick this. So I pick this BD. All right, so I put it back here in the tree. I have BD formulated, and it's now in the tree. Now it's no longer in my frontier, this edge now. Then I'm going to find D and B, the vertices, and I'm going to merge the sets if they are not already together. So I got D here, and I got B here. They're independent sets. I'm going to, I found them, and I'm going to merge them. I'm going, what do we call merging when sets are involved? We call that union. So I'm going to create a union between these two sets. So in my set now, I'm going to have B and D as items in the set. So this guy and this one, now they are no longer part of my set here because I have B and D here. Let me try to draw them with a blue pen just to show you what's going on. So B and D, and then we have A on its own, and we have C on its own, like that. Good, let's go on. Then now we have done that, and we have removed the edge with 2. Now we find the next minimum wedge. So the next minimum edge is DC, which has the value of 3. So we look for DC. BD is on its own set. C is on its own set. So now we're going to create DC here. Okay, by creating DC, we found BD to be on its own set, C to be a set by itself, so we'll merge them. We have B, we have B, we have D, and we have C. And now we have A here on itself. Okay, now we keep going. Now, which is the next one? So we remove this guy. So now we want to look for something else, which has a minimum weight. AD has 4. So we're going to look at AD. Well, AD, A is a set by itself. BDC is a set by itself. So we're going to pick AD because they belong to different sets. So we pick AD there. And now this, our set, looks like this. We have A, we have B, we have D, we have C, and so on. So we can stop here. Why can we stop here? Because we no longer have any independent sets. We have just one set having all the vertices, and the vertices have all been considered. So this is 4, this is 2 and 3. Again, the value of IMST is 9, just like what we saw using the Prim's algorithm. Okay, so look at what would have happened. So supposing, so this one is gone now, this guy. Let's imagine that we had picked also AB. Now, if when we try to go and pick AB, we come here to look at our set and we find that A and B are in the same set. What that tells us is that if we were to join A and B here, if we were to join A and B, then essentially we would be creating a cycle. And if we create a cycle, then this is no longer a tree. Okay, this is no longer a tree. So we are essentially utilizing a data structure that allows us to essentially not create cycles or even be able to detect cycles. This data structure that we use to be able to do this is called disjoint sets. Coming from the name, it's called disjoint set with disjoint sets and so on, or we call it unified. Okay, and essentially the idea is that we are fighting the sets and then unifying them in order to create the sets as we go on. And then we'll be able to know if we are going to encounter a cycle, if when we try to join two things, we find them to be on the same cycle and so on. So we're using unified to do our work here. The edges here, we could have maintained this using something like a priority queue, using a heap, a binary heap, some sort of a heap. Okay, we could use a heap to keep these things. And essentially, we just want to keep up, picking up the minimum cost and so on. Similarly here, for our Prim's algorithm, our frontier could have been a heap where we are just picking up items and so on. Or it could be unsorted array, and then we have to keep searching for the items that we have. Now, so in summary, regarding this, we have considered minimum spanning trees. And we have considered two techniques, Prim's algorithm and Kruskas algorithm. And if you consider these techniques, algorithms, and if you consider these techniques, this is what we are doing. we came up with a rule of the thumb. So we have here rule of thumb, that we came up with. And this was always pick the edge with the smallest weight. With the smallest edge. Always pick the edge with the smallest weight. That's what we are doing the whole time. Always pick the edge with the smallest weight to form a tree. Our belief being that by picking this edge, let's think about it like an edge, or considering one edge, considering just one vertex, and its adjacent vertices, essentially considering the edges connected to a particular vertex, is a sub-problem. Let's think about it as a sub-problem. It's a sub-problem. Essentially, just creating one edge of the tree is a sub-problem. In our case, then, our belief is that a local solution, which is optimal, a local solution, or I would say a local solution optima, will lead to global optimum. This is what we are thinking. Our local solution or local optimum will lead to the global optimum. Okay, so we come up with a rule of the thumb. Always pick the edge with the smallest weight. That's what we are doing in our case here. We came up with a thumb. Always pick the edge with the smallest weight. And our belief is a local solution or a local optimum will lead to the global optimum. That's our belief. A local optimum will lead to the global optimum. Now, in both techniques that we have considered here, Prim's and Kruskas algorithm, that's exactly what we are doing. Now, these properties here are properties of greedy algorithms. Greedy algorithm. These are properties of greedy algorithm. So the problem really has two parts. We are having a sub-solution or a sub-problem. We are thinking about sub-problem at a local level. And our sub-problem, for example, in a minimum spanning tree, is this idea that we just need to consider the edge, just one edge that we are going to add to the tree, because the vertex will need to be added to a tree. And just thinking about that particular edge that we will need, then that's a sub-problem. And we believe that a solution to that local problem will lead to the global optimum, will lead to the global optimum and so on. Okay. Now, important thing here is this is what is called optimal substructure of the problem. Okay, optimal substructure of the problem. Okay, optimal substructure of the problem. The idea that a local solution will form part of the overall solution to the problem. A local solution, the one we have, this sub-solution or solution of the sub-problem, will form or will be forming part of the solution set to the global problem. So here, when we consider just one of the edges, for example, BD, which was 2, that is going to be part of the overall solution to the actual problem that we have. Okay, now let's see this again. Let's see this, we take a few minutes back and we consider this again, greedy for single source shortest path, the one now we used with Dijkstras algorithm. Let's see that again, Dijkstras algorithm. Now, with respect to Dijkstras algorithm, let's use the same graph that we have here. This graph is A, B, C, D. And this is 5, this is 4, this is 2. This edge was 6 and this edge was 3. Now, remember, single source shortest path problem is not a minimum spanning tree problem. Essentially, we're given an arbitrary point or one that we can select. For example, a starting point could be A, and we are interested in finding out the shortest path from A to all the vertices in the tree, okay, to all the vertices, to all the vertices in the graph. Okay, so remember also, because this is an undirected graph, we do not want to come back to to any of the vertices. So we always need to maintain an explorer set, which tells us that we have already visited those things and so on. Now, in our previous conversation regarding Dijkstras algorithm, again, we start up with a single point, for example, A. And when we start off with A, we label it as having a value of 0 because the path from A to A is 0. And then for all our vertices, we give them positive infinity, essentially because we want to minimize those distances. So we start with a big number and we want to become smaller and smaller and so on. Now we could have written this as this. Could have drawn all the things A, B, C, and D here. This is 0, and then we can have positive infinity to every single one of them. And essentially, we came up with idea of a relaxing property. We're going to think about the key or the value to any one of these. The key of a particular vertex V, the key of a particular vertex V is going to be given by the key to the previous vertex, key of U, or the value of U. Maybe I should put like this, instead of these, I should call them D. So the D of V is the D of the previous one plus the weight between U and V. And this is the case if at the moment, if and only if the D of V is greater than D of U plus U to V. And we say that this is called relaxation property. Relaxation property. Say that this is going to be called relaxation property. So now, so we have this guy now looking like this. And what are we doing? So we consider now from A, we go to all the vertices that A have. From A, we go to all the edges incident to A, edges which are incident to A, AB and AD. So from AB, this is going to be 0 plus 5, 0 plus 5. So we update B, and we say this is going to be a 5. So this is 0 here, this is 5. And then A to D, this is 0 plus 4. 4 is smaller than infinity. So this is 4, and this is still infinity. Something like that. Okay, so A now, if I was playing with a cross set here, letting me call it cross set. The cross set now here has A. We are done with A. We have processed A. Now, which one has the lowest value? D has the lowest value. So remember, we are also going to search for the one with the lowest value. So the one with the lowest value is D. Okay, so we go to D. Now, D has 4. And then we are going to now check across all the vertices, all the edges which are incident to D. So we have DB, which is 2. 2 plus 4 is 6. 6 is bigger than 5. So we are not going to update B. Okay, we are not going to update B. And then we go to 3. So D is 4. 4 plus 3 is 7. So we're going to update C with 7. So this is 0, 5. This is 7. And this has already been seen. So D is here. D has already been visited. Okay, now D is visited. So we are done with it. Then the next thing now is to get the smallest one. So we are choosing between these two. And the next one is 5. Now 5, we can't go back to D because D is already in the cross set. 5 plus 6 is 11. 11 is bigger than 7. So we can't pick that one. And essentially we cannot update C. So we are done. B is already there. B is considered. Now, the last one is C. Now, C, all the other vertices have been included, so we can go back to them, and therefore our final answer looks something like this. From A to B is 5. From A to D is 4. And from A to C is 7. By following A to D to C is 7. That's the most optimal way of heading there. You'll notice by running these A, D, B, C, and so on would have been more computation that will not yield anything. Now, important here is that for any particular sub-solution, so we considered A, and we considered A as a sub-problem, and the sub-problem was from A to its vertices. Why are we considering that as sub-problems? We are thinking that, from A to go to future ones like C, it would have depended, from A to C would have been dependent of from C to D and B, right? To D and B. So we are going to consider that from A to the vertices near it as a sub-problem, right? So we have a substructure problem or a problem such that we can make sub-problems out of it. We can have those sub-problems, coming, of this nature, where we can be able to solve, from one vertex to another. So we have some sub-problems. And then we have this idea that we talked about of optimal substructure. And essentially what to say is by determining the solution to the sub-problems, for example, the sub-problems of A to B to D, those one will form the solution that eventually tells us how far it is from A to C and so on. So we have an optimal substructure. And again, here, the optimal substructure means that the local or solution to a sub-problem, solution to the sub-problems forms the final optimal solution. So also this one has that kind of things. Again, we came up with a rule of the thumb. The rule of the thumb was saying, hey, we're going to establish A, we're going to update all the vertices, and then we're going to choose the one that has the minimum cost and so on. So that's the whole essence of solving problems using a greedy approach. Come up with a rule of the thumb, formulate an optimal, and be able to prove the optimal substructure to the problems. Now, you may have noticed that for all these Dijkstras algorithm, the Prims, and the Kruskas algorithm, all of them using greedy approaches, that I did not show a proof for correctness for it. This is because those notes are on the Canvas page, and I would like for you to look at them and be able to formulate that, including the actual notes. They are there. And also the other thing that I did not do was ask for running time and so on. Things to consider is this, what data structure that I'm using. Here you may have noticed, because I'm picking the lowest, I'm using a priority queue. For example, in Dijkstras algorithm, I'm using a priority queue. In Prims, I'm also using a priority queue. And then in Kruskas, I'm using unified. And I'm also using priority queue for the set of edges that I have. And then based on those, you will be able to compute the running time for the techniques that we have there. Okay, so we have been speaking now for about an hour. So what we're going to do is you are going to do some exercises now. Exercises. There are two of them. There is number one. We can start off number one with the, with a 5 minutes multiple choice. 5 minutes multiple choice. So you can have that now. 5 minutes multiple choice. This is going to be on Socrates. Okay. Possibly I couldn't be able to show that in a minute. Socrates. Go to Socrates. And then from Socrates, just put in the name as Moura. and you'll be able to see that in a minute. And then number two, once that has been done, you can have another 10 minutes, and these 10 minutes, these are going to be longer ones. You're going to compute with prims, you're going to do with Kruskas, and then come up with a final determination for these kind of things. So we're on top of the hour. We are going to congregate back in about 15 minutes when you have done this, work now. Thank you. Thank you very much. Hopefully you enjoyed that bit. In our earlier conversation, we talked about this Dijkstras algorithm and the way it was solving this problem by picking up, different things, different subset to the solutions and so on. Now, I want us to consider another problem, for example, still using, the Dijkstras algorithm. Let's see this. Supposing we had, so again here, single source shortest path problems. And what I want to do, I want to grow this graph. A here, then we have maybe something like a B here. Then we have C. Let's just have four things here and so on. And so A to B is 4. Let's make it direct. A to B is 4. A to C is 2. And B to C is -2. So supposing we have a graph that looks exactly this, but this graph has some negative weights. So this graph has some negative weights. Now, negative weights in the graph are possible, essentially because weight could represent a lot of different relationships, right? And vertices could mean also different things and so on. This could have been some sort of loss, and this could have been some sort of loss and so on to something. Okay, so it's possible for graphs to have negative weights and so on. So the first thing we should ask ourselves is, how would Dijkstras solve this problem? Dijkstras algorithm. How does it solve this problem? Now, I want you to spend a few minutes and to consider what Dijkstras algorithm would give it. And specifically, you want to think about the solution generated by Dijkstras. Is it going to be a correct solution? Let's think about this. So let's run Dijkstras algorithm, and we say start at A. Now, if you start at A, let's draw this. This is A, B, and C. Dijkstras from A to B, so, well, it will start off with this as being 0, then infinity, then infinity. Then A now is 0. We're going to consider the two adjacent things to A. A to B is 4. So 0 plus 4. So remember, this is 0, this is infinity, this is infinity. So 0 plus 4 is 4, and 4 is smaller than infinity. So we are going to relax that edge. So this is 4 now. And then A to C is 2. 2 plus 0 is 2, and 2 is smaller than infinity. So this is 2. Good work. So if we had some sort of cross set, our A would be here, and A is already sort of finished. Nice. So now we go to the next shortest one, which is C. So we got C here. Now we visit C, and now we visit C, and C is a 2. Now, so from C, we can't go back to A because this is a direct graph. We can go back to C, to A. From C, we can go back to B also because it's also a direct graph, and therefore C has been considered. From A to C is 2. We are done. Now, let's consider B. From A to B is 4. So this B has 4, so we select B to do that. Now, from B to C is -2. But unfortunately, we can't go back to C because C is already in the visitor set. So we are done here also with B. So the answer that we get from Dijkstras algorithm, Dijkstras says A to B is 4. And then A to C, S to C is 2. Optimal or not? Well, now let's think about it. Well, from A to B to C is 4 minus 2, which will be 2. There is a root. A to B to C is equal to 2. But Dijkstra gives, but Dijkstra will only consider this. Dijkstra gives 2. Dijkstra, well, this is the shortest one here, so to say, so maybe, and so on. So maybe that's not a problem. But if C was 3, for example, supposing C was 3 here, I'm just giving as an example. If C was 3, Dijkstra, so this would have been 3, sorry about that. If C was 3, for example, if C was 3, then Dijkstra still would have given us 3. A to C would have been 3, yet A, B to C is actually 2, right? It's actually 2. But Dijkstra gives us 3. So definitely not optimal. Definitely not optimal, right? So Dijkstra would not have seen these because it's not optimal for us to see, and so on, right? So that's a good question to ask ourselves. What should we do? That's a question that we should ask ourselves. What should we do? What should we do given these kind of things? So I think the moral of the story is to say that in graphs involving negative weights, like the graph that we have seen here, the graph including negative weights, Dijkstra might not always give us the correct solution to the problem that we are looking for, might not be able to give us the correct solution to the problem that we are looking for, to the solution that we are looking for. So another technique is called BellMan-Ford algorithm. BellMan-Ford algorithm. And now let's consider the same. We had A, we had B here. This was, let's go back a little bit. This was 4, and this was 3. C is 3, and this minus 2. So the way this technique works, the way the techniques work is going to consider many different things. Now, remember, if we wanted to know the solution to this problem, the correct optimal solution, one of the things we could have done is brute force, right? And what does brute force mean? Brute force means that we could have considered all the possible paths from A to C and all possible paths from A to B. Consider all of them. Consider all possible paths from A to all vertices, Consider all possible paths and pick the best. Pick the one with minimal or minimal cost to it, right? That's what we would have done before. That's what we've done before. Well, one thing we might think about is what will be the longest one? What will be the longest one? Longest path. Now, let's try to convince ourselves that the longest path from A to all the vertices, from A to all vertices, to a particular vertex, to all vertices, the longest path, that longest path from A to any of the vertices here, any longest one should go through all the edges or should go through all the vertices. That's the answer. Should go through all the vertices. So the longest path from A to a particular vertex must hop through all the vertices possible. So longest path must go from V minus 1 edges, right? The longest one should be able to go from V to minus 1 edges and so on. So essentially, for example, A to C has only 3, just at one edge. A, B, and C, 2 edges, and so on. So the longest one that we could consider in terms of, even if we did not consider, actually, that's a good question. It might not really be the longest in terms of the total weight, but in terms of the total number of edges. The one with many, many edges, the one with multiple edges must go through V minus 1 edges. Yeah, might go through V minus 1 edges. Now, if that's the case, then, so the longest one, or the one with multiple edges, must go through V minus 1 edges. So that tells us this. Supposing we were to repeat going through this graph or relaxing the edges V minus 1 times. Okay, so moral of the story, consider all edges, and consider all edges and relax using the relaxation property, using the one we saw in the Dijkstra relaxation property. V minus 1 edges, V minus 1 times. Okay, so consider all edges and relax them using the relaxation property, the way we saw from Dijkstra. Do this V minus 1 times. Okay, so important here then is just to write up the edges in similar manner that we would have done when we did the Kruskas technique. So what are our edges? We have AB, we have AC, and we have BC. These are the edges that we have. So how many times must we repeat this? We must repeat this. The relaxation, sorry, my screen went off there just for a minute. So let me try to bring it up for just 1 minute. Consider this. Just bear with me. Okay, I'm sharing a new screen now. Okay, here, this is where we are. Okay, so let me go back here. Okay, here we are. So we're going to relax these edges. Okay, we're going to relax these edges that we have here, and we are going to relax them V minus 1 times. So what's V minus 1 times? V, the coordinate of V is 3. So we have 3 vertices. And we want to relax these 3 vertices minus 1. So we just need to repeat this whole process 2 times. So we're going to relax all edges, in our case here, 2 times. So let's see what happens. So we go to AB. It doesn't matter where we start, right? Because we just want to relax all edges. We must consider all of edges, okay? So we are not just picking up the vertices with the best value. We're essentially just thinking about all the edges and relaxing them. Essentially, by doing so, we'll have gone through from one vertex to all the other vertices by considering all combination of edges that vertex could go through. Okay, let's think about it. A to B is 4. So this is 0. This is infinity. This is infinity to start with. So A to B is 4. 0 plus 4 is 4. So this guy is 4 now. We do that by picking up AB. Already consider this is times 1 times pop 1. Then, so this is 4. But instead of picking the 1 that's 4 and then working with it, we're just going to consider again A to C. A to C is 3. So A to C is 3. We considered it. So this guy becomes 3. And then consider B to C. B to C is minus 2. B to C is minus 2. So 4 minus 2, 4 minus 2 is 2. So we put this as 2 here. And we are done with one step. So remember, we must consider all edges. This is key to this technique working. We must consider all the edges. So we are not putting these things into some sort of closed set, and therefore we cannot visit them anymore, we are going to consider all the edges and relax the edges based on this idea that we must repeat this phi minus 1 times. So we have considered that now. Then the second time, again, we consider A to B. So we consider AB, AC, and then BC. We consider all of them. And because we are considering them, sorry, I think the share did not work. And because we are considering them, just bear with me from a minute. I just want to make, okay, yeah, I believe it's sharing. So because we are considering all the edges one by one, these two should work. So let's do again. A to B is 4. So this B does not change. A to C is 3, but 3 is bigger than 2. So we don't update C. And then B to C is minus 2. So 4 minus 2 is 2. So we don't update C again. So this technique says we do this 2 times. Well, there was no change on this time, and therefore we are done. Now, what does it say with using this technique? It says A to B is 4. It says A to C is really A to B to C, and therefore our answer here is 2. Remember, the power of this idea is that we are going to think about the multiple ways we could solve this problem. And then we are going to keep these subsets of solutions one by one. We are going to keep them and repeat these multiple times. Repeating multiple times essentially is telling us this: to consider all the problems, to consider all possible solutions. But here we are doing it a clever way. Consider all possible solutions, consider all of them, and then at the end, we'll be able to generate the best one. Consider all these and the best one. So this technique has 2 things. Number 1, we have the idea of optimal substructure. Okay, optimal substructure. You may have seen optimal substructure when we talked about the greedy algorithms. And this is true for this technique too, because the solution that we derive to the sub-problems that we have before, that solution forms part of the global optimum. So we have optimal substructure. The next thing that we observe with this one, we have some sort of overlapping sub-problems. Let me put it like this: overlapping sub-problems. Okay, so we solve the first time, and then we come back and we solve the next. So we consider the first one as sub-problems, not necessarily repeating themselves, but as sub-problems that we actually solve. And then we come back and we are able to solve the same. So for example, we solve A, and then essentially we repeat the exact same thing that we did with A with B, and then we just keep repeating those as well. Okay, as well. Now, what we're also doing here is we are saving the results. We are saving the results. Either save the results, save results of sub-problems, save the results of the sub-problems, and then combine them, sub-problems, and combine them later. Combine them to form the global, to form optimal solution. to form optimal solution. Okay, combine them later to form optimal solution. That's what is happening here. Now, so this is BellMan-Ford. This technique, by the way, is called BellMan-Ford, the one we talked about, BellMan-Ford. And in this BellMan-Ford, these guys here are properties of dynamic programming. Okay, these are properties of dynamic programming. So important here, the properties of dynamic programming, the problem should have optimal substructure. The solution to a sub-problems will form part of the global solution. The problem must be overlapping sub-problems. So not necessarily that we are solving the same sub-problems, but we are solving, part of the problems. We are going to see this, and then we can save the results of the sub-problems, and we combine them to form the optimal solution. And that's what we did with this BellMan-Ford. Now, we're going to see another example, possibly of BellMan-Ford, so that we can be able to understand this even better. Let's see whether I can come up with something. Let's imagine this is A, so this is B, this is C, this is D, maybe this is E, who knows? This is E, and then I'm going to, we can put some things like that, and then can do that. Okay, let's have a graph that looks like this. So this is maybe 3. This must be 4. This must be 2. Okay, 2. Maybe we could have, something that says that we can go back. We can go back here. This could be something like 10. Let's actually make it minus 10. Yeah, minus 10. It could be 2. And maybe this could be 3. This could be 6, and so on. So if we have these now, we have 5 of them, right? We have 5 vertices and so on. 5 vertices and so on. So demonstration again of BellMan-Ford. Okay, now with this BellMan-Ford, again, what did I say we do? We take all the edges here, A and B is an edge. A and E is an edge. A and C is an edge. A and C, so A and B is an edge, A and C is an edge. We have, no, we don't have A and C. We don't have that one. Okay, then for B, we have B and E as an edge. B and E is an edge. Then you have E and C as an edge. And then we have E and C. And then we have, for C, we have C and D, or C and A, an edge. We have C and D as an edge. And we forgot one more, which was E and D as an edge. E and D as an edge. So we have these edges here. Okay, now, so that's good. So we have them there. So essentially what we said, we are going to relax these couple of times. How many times? 1, 2, 3, 4, 5. We're going to degenerate these 5 minus 4 times. So we're going to do this relaxation, V minus 1 times. So 5 minus 1 times is 4 times. We're going to relax this 4 times. We're going to pick each edge, and we're going to repeat this 4 times. So let's do the first one. So we assign everything here, infinity, infinity, infinity. This guy is infinity too. And I'm going to take a blue pen, and we're trying to do this. So A to B is 0 plus 3 is 3. So this guy gets updated to 3. And then A to E is 2. So this guy gets, sorry, yeah, A to E is 2. So this guy gets updated to 2. And then B to E is 4. So 4 plus 3 is 7. So we don't update E. We just leave it like the way it is. E to C is 2. E to C is 2. 2 plus 2 is 4. 2 plus 2 is 4. So this guy, we update it to 4. Okay, so we considered A, E, B is, in fact, let me not label them so that we can be able to come back. A, B, A, E, B, E, E, C, we did E, C. We do C, A. C, A is minus 10. So this 4 minus 10, so that's minus 6. So this guy now becomes, instead of that, becomes minus 6. And then C to D is 3. So 4 plus 3 is 7. So this is 7 now. And then E to D is 2 plus 6, 8. So we don't deduct D. So we are done. Okay. Then so we have done the first part. Second time, we need to do this 4 times. Second part, A to B is minus 6 plus 3. That's going to be minus 3. So now this is minus 3. Okay. And then, so this second time, A to E was 2. Now it's minus 6 minus 2, which is now minus 4. So this is minus 4. Okay. E to C is now minus 4 and 2, which is minus 2. So this guy is minus 2. C to A is minus 10. So this is minus 12. Minus 10, minus 2. This is minus 12 now. C to D is 3. 3 minus 2 is 1. So this becomes 1. E to D is minus 4 plus 6 is minus 2. So this guy becomes minus 2. Sorry, 2. No. So we can update this. Minus 4 plus 6 is 2. And this is already 1. So we don't need to update that. So that's the second time. We do it that time. Let's see what's happening that time. So in that time, A to B is minus 12 minus 3. This is minus 15 now. Okay. Now, what's happening? A to E is minus 12 plus 2, which is minus 10. So this guy now is minus 10. B to E, B to E is minus 15 and 4, which is minus 11. So this guy will become minus 11. Okay. C to A, E to C is now minus 11 and 2, which is minus 9. So this guy becomes minus 9. And then C to A is minus 10, minus 9 is minus 19 now. And then C to D is 3 and minus 9. So this is minus 6 now. And then E to D is minus 11 plus 6. That's minus 4. So this will say as minus 6. We repeat the last time. A to B is minus 19 plus 3 is minus 16. Yeah, that's minus 16. And then A to E is 2 minus 19, that's minus 17. So this guy becomes minus 17. And then B to E is minus 16 minus 4, which is minus 12. So this will stay as minus 17. And then C to A, sorry, E to C. E to C is minus 17 minus 2. So this becomes minus 15. And this becomes minus 25. And then C to D is 3 minus 15. So this becomes minus 12. And then E to D is minus 17 plus 6. That's minus 13. Oh, no, that's minus 11. So this will stay the same. Okay, so at the end, we have this. A to B is minus 16. Okay, minus 16. And then A to E is minus 17. Essentially, in order to form to form this answer, we are moving from A to B to E to C to A, and then going back to B. This is what forming as an answer. But why is this answer looking like this, by the way? So minus 17, we can say that A to C is minus 15. A to D is minus 12. And A to C is already done. Okay, yeah, already everything is computed. What would happen if we were to do one more time? So this is what we did we did 4 times. So what would we do if we did 5 times? Well, this would be minus 25 to minus 16. So that will change still. So the answers will keep changing if we did this. So there are changes. There are changes. There are changes even after V minus 1 iterations of the algorithm. There are changes even after V minus 1 iterations of the algorithm. There are some changes going on. So let's interrogate this to see what's going on. It looks like we can be able to move from A to B to E to C back to A. We are able to go back to this because we are only considering vertices, by the way. Sorry, we are considering edges. We're able to do this because we are relaxing each edge. We're able to do that. And there's also a problem here. Let's see what the problem looks like. When I go to A to B, what is the total weight? 3 plus 4 plus 2. 3 plus 4 is 7. This is 9. So I'm considering this. Going this way and this way and coming back. This is 3 plus 4 plus 2 plus minus 10. So that's minus 1. So there's a negative weight cycle going on. Okay, there's a negative weight cycle going on. Also, actually, from A to E, and then to C, and then back is 2 and 2, 4, and then minus 10. That's minus 6. So there is negative weight cycle. So what is this technique? After we do V minus 1 times, we realize that we keep changing, which essentially tells us there is negative weight cycle. There is negative weight cycle. There's a negative weight cycle. Now, with negative weight cycle, there's a negative weight cycle. What that means, this idea, this negative weight cycle, is that we cannot be able to compute correctly, even using BellMan Ford, we cannot be able to compute correctly the shortest path of this particular graph because it's a negative weight cycle. But what BellMan-Ford does, it helps us to be able to detect negative weight cycle. Helped us, BellMan-Ford can help us detect negative weight cycle. Okay, so we're going to stop there with BellMan-Ford. So BellMan-Ford is a technique, is a dynamic programming technique. It's a dynamic programming technique to solving single source shortest path problems. It's versatile in the context that when we have negative weights, it can help us do the same, something that the Dijkstras algorithm could not help us do. Also, we have to notice that when we have negative weight cycles, BellMan-Ford technique will not help us to solve that problem, but it will help us to detect it. Okay, so that's an important thing to actually know. It will help us to detect it, although it will not be able to solve. So that's the important thing to have and to consider, the things that we have here. Now, we are going to take, we're going to now do some sort of problem solving where we are going to use Dijkstras algorithm and BellMan-Ford. So wait for that. So problem solving now. Problem solving. Dijkstras. Plus BellMan-Ford. Okay, get your papers and let's work on these problems.